presentation, and well, actually, this is a first attempt to write down. I mean, to try to translate much of the forcing machinery in terms of Grothendieck sheaves. And
scusa Matteo, se muovi forse un po' lo schermo perché ti si vede soltanto la fronte.
Ma non vedete lo.
Sì,
allora,
ma
il problema è
di
questo.
fianco si
The problem is the following. I have to write on a tablet. So either I do like this, that I'm hovering over the sheet of paper over the
go.
desktop, or I do like this, which is the standard position, and probably you just see my front.
No problem, go.
Okay, so essentially the attempt is to connect the forcing machinery and to formalize it in effective way in terms of in the language of sheaves and categories. And clearly, I mean, there has been already a lot of work in this direction, but I think that to some extent the venue that has been mostly followed is via intuitionistic logic, and I'm following rather an approach with classical logic, which as a byproduct limits the range of the type of sheaves that we are going to be interested in, because the fact that one sticks to classical logics brings in a lot of restriction on the type of sheaves one is then going to consider. But I think it's still I think it can be of interest because those sheaves are not so exotic. I think they form a sort of universal family among the class of sheaves if one has the right notion of, let's say, embedding of sheave into another sheave. So let me start from scratch. And the idea is first to introduce the notion of Boolean valued model. And what is it? Well, essentially, one replaces Boolean values to 0, to false and true. So the idea is let tau be a first order signature. We assume that. Do you see everything fine? Is the writing okay?
Perfect.
So I stick to the convention that I consider just relational signatures. So I don't want function symbol. This just because it makes somewhat more complicated the Boolean semantics. But it's if one wants, one can also add the function symbol, and there is no loss. I mean, it's just making things more complicated without helping with intuition. And we know that function symbol can be subsumed by relation symbol at the price of complicating a bit the expression, the first order expression. So what is the idea? And we have also a Boolean algebra. And then we define M, which is a domain, and then the interpretation of function symbol. Sorry, and interpretation of constant symbol. And well, clearly Cj is just an element of M for all j, small j and big J. But what is interesting, what is the interpretation of the relation symbol? Well, first we have a interpretation of equality, which is a binary map from a binary a map from couples into the Boolean algebra, and which interprets the equality. And we have then similarly interpretation of that goes to the arity of the relation symbol, M to the arity of the relation symbol, and it assigns an element of the Boolean algebra. Sorry, here I'm I'm again, so I have A1, A to the ni, and this maps to the Boolean value of R evaluated in those elements.
You're not writing anymore. Oh, yeah.
You don't see what I'm writing?
No,
Yes,
there is a little bit, sometimes there is a delay.
There is a gap in the connection. Apologies. Okay, so we have this interpretation. In order to make everything consistent with the intended meaning and the expected meaning of equality and relations, we have the following constraint. So first constraint is that equality on identity gets truth value 1, so it's true. And then that equality respects symmetry. And then we need also that equality is transitive. And also we need that equality respects relation commutes with equality, so that there is a congruence relation between the relation symbol and the equality. So if we have this set up, so sorry, this is not a good notation. Aj equals bj, which Ri of so we have that this is below Ri of B1, B, and I. So with this constraint, we ensure that the semantics of first order logic is correctly evaluated in a Boolean valued structure. I just sketch what happens for semantics. Well, let me say it for we consider tau union M as the new signature. So we add constant symbol for the elements of M, and I give the semantics for phi a sentence. So I omit the interpretation of formula with free variables. This is easily extended to formula with free variables of tau union M. What one does, well, we assign well, phi is phi if phi is Ri A1 ANI. Okay, so I have my formula, sorry, my atomic formula. In this case, I already have my maps given by those requests, by the interpretation of the function and of the relation symbols. And then I use the, sorry, I am not entirely familiar. So if I have, not phi, the Boolean value, well, I can use the operation on the Boolean algebra, and I'm no problem. And similarly for the conjunction, implication, and the relevant case is the existential case. So Px A, and in this case we let the sup over A in M of P A. Sorry, P A. Let me. Do you see everything fine?
Yes.
Okay, I have a problem. Well. Okay, so everything clear so far? No, I guess this is rather standard. There's nothing particularly smart. Okay, and the unique point, delicate matter is that in order that this definition makes sense, one needs some degree of completeness of the Boolean algebra, because we are taking a sup over an infinite an infinitary set, so in principle it may not exist. We may, for the purpose of this talk, assume that the Boolean algebra is complete, but otherwise we just require that it has the degree of completeness needed for the definition to work. So let me give an example, a simple example. L infinity of R. What is this? Well, this is very well known. It's the function from R to R, such that f is essentially bounded and measurable according to Lebesgue measure. Okay, and well, what are the Boolean values? Well, what is the Boolean algebra? Here I have to declare what is the Boolean algebra. The Boolean algebra, let me take MALG, which is Lebesgue measurable sets modulo null. And then I can assign f equal g, the equivalence class of the set of reals where f of x is equal to g of x. And I can do this for any reasonable function or relation symbol. What matters is just that the operation or relation I'm considering as a measurable graph. So in this case, I'm taking relations or functions which are even continuous, but I don't need to be so restrictive. I can just put any measurable relation of and one check that this definition works for the, well, here I'm considering the language minus, plus, and well, plus seen as a ternary relation, not as a binary operation. Okay, is everything clear so far?
Perfect.
Okay, and where does the Grothendieck approach kicks in this well, if we think of L infinity R, well, this is naturally seen as a global section of a presheaf, which presheaf I have a problem, sorry, apologies. There is a problem with my, oh, no. I don't know why it has eaten a part of my screen. Okay, what is the presheaf? Well, the presheaf is given by L infinity A contained in R, A measurable. Okay. So the idea now is to connect this notion of Boolean valued model, which is just a natural generalization of first order structure in the classical sense, to the notion of presheaf, and to see what can be said in this correspondence. Okay, so let me just first informally define the functor that relates a presheaf to a Boolean valued model. So we have a presheaf, which is an operator, well, a functor that to a topology, so X now topological space, and I want to associate to this pre-sheaf a Boolean valued model. So for the moment, let me omit so I'm considering just values in set, not values in some, let's say, algebraic category like groups or rings or whatever, in which case I should plug in the relevant language. While in case of set, I just need to give a meaning to equality, but it's clear that what I will do with equality then easily transfer to the algebraic operation or to the relation that one is interested in considering if the target is not set, but some richer category of objects. Okay, so we take what is the Boolean algebra? The Boolean algebra is given by the regular open sets. So topological space, we attach the regular open set. This is, I guess, the standard definition if one is interested in classical logic. And what is the Boolean valued model? Well, we take f of x, so let's say m of f. So this is the functor, and I want to attach a Boolean valued model. This is the domain, f of x, the global section of the pre-sheaf. And then I have to interpret equality. So equality in m of f. What is it? I will say that what is the degree of f equal g? F and g are global section. Well, I say that this is the it depends on, well, the abstract definition is the supremum over this Boolean algebra of the element A in the topology, such that F restriction to A is equal to G restriction to A. Okay, and actually, sorry, this is apologies. This is not entirely correct. I have to correct one. So it's regularization of A. So because A is just an open set, and it may not be regular open. So I'm interested in, and I might have the situation in which my F and G will not overlap never on a regular open set. They will just overlap on some non-regular open set. Well, but I consider I'm interested just in this non-regular, in this overlap over non-regular open set. I make the union over all these non-regular open set over which the two function overlap, and then I take the regularization, and this is the value of equality. And the similar definition will work for arbitrary relation or function symbol of the language. Okay, and this shows that pre-sheaves naturally corresponds to Boolean valued model. But we want to go the converse direction, and this is a bit more elaborate. There are various approaches, and I will take one which identifies sheaves with bundles. And so I want to associate to a Boolean valued model a bundle. So this association is not going to be functorial. Well, it's not going to be, it's going to be functorial, but it's not going to be an exact correspondence, because the exact correspondence is a Boolean valued model with pre-sheaves on compact disconnected Hausdorff spaces. But to have an idea of how this how are we going to associate to a Boolean valued model a pre-sheaf, I follow this pattern, which is the following. I need to expand more the theory of Boolean valued model. So let M be valued. And F contained in B a filter. And we set for B valued for tau. So I have my signature for R belonging to the relation symbol. I set R of the equivalence class of, well, I have still to define these objects. This I will define soon. In this quotient structure, in this quotient algebra, well, I just take the equivalence class of in the quotient of R of tau 1, tau 1. And what I should put here, I put the sigma such that sigma equal to tau 1 belongs to F. Okay, so one can check that due to the fact that F is a filter and due to the constraint we put on the interpretation of equality, this relation of asking that two elements are in the relation if their equality belongs to the filter is an equivalence relation, and it's actually a congruence relation with respect to the interpretation of the relation symbol. So everything behaves correctly, and this definition is well posed and passed to quotient. Okay, is this clear? Should I expand more on this part?
Fine.
Okay, then what happens if G is contained in B is ultra filter? Then what happens is that M mod G is a B mod G, which is 2 modal. So for tau, so I recover by passing to the quotient with an ultra filter, I recover a Tarski structure. Okay. Okay, so let's see, just to understand what happens concretely with some examples. So let me go back to the L infinity of R. So if I take the trivial filter, which is just made of the equivalence class of R in MALG. So recall that my B was MALG, a measurable algebra, which is measurable modulo null. And if I mod out L infinity R mod F, this is what it's studied in the analysis courses. It's the space of essentially bounded measurable function up to difference on a measured zero set. So here we are considering the equivalence classes of functions, not the functions themselves. Okay. So this is in case I take a trivial filter. And what happens, sorry, it's the first time I'm giving a talk with the iPad, so I'm not particularly brilliant at using it. So what happens if I take a ultra filter? So if I do L infinity R mod G, G contained in MALG ultra filter. Well, then I get FG, F in L infinity R, and this can be seen. This is for many languages. I mean, for many languages. I mean, for example, the language I consider in the beginning, it is an elementary extension of R. So it is a non-standard copy of for example, for tau equal minus plus times 0, 1, But essentially here you could put any Borel relation, and you would maintain the elementarity relation of the structure. Okay. So essentially, you see this particular case is giving us a different mean to produce, let's say, superstructure of a given Tarski structure. If we use a Boolean algebra, and we, I mean, well, let's not expand too much on this. So for this particular example, it's clear what's happening. And it can be generalized abstractly to any to a very large framework, which I will not explore here. Okay, but then how should I associate to a Boolean valued model a bundle? Well, the idea is these are going to be the stalks over the base space. So the base space is going to be the stone space of the Boolean algebra. The stalks are going to be given by this Tarski quotient modulo the ultrafilters in the base space, and my Boolean valued model will correspond to a certain amount of global section of this bundle. So I define the bundle. Given a B model for tau, and for the sake of simplicity, I'm considering just I'm just making the definition meaningful and sound for the equality, and for the rest it demands a bit of effort, but it can be done. And we let the BM to be the disjoint sum over the stone space of B of the sets, those Tarski structure for G that, well, let me write it more correctly. Okay, so this is the bundle, and I have to say when I do identify points, so what I say that Fg is the same as Hk if and only if G equal K and Fg equal Hg, which amounts to say that by definition, this amounts to say that H equal F is in G. Okay. So there are, I mean, already from this way back and forth, one is has certain questions that arise in one constant and can be translated in the other. So first question. When is F of B of M? Sorry, this was the, I forgot how I defined the functor. Apologies. Apologies, one moment. Okay, so it's not F of B of M, but so when is so this is a bundle. Well, the bundle, let's say here I have to be sloppy. Apologies. B of M seen as a sheaf over stone B. So I consider the pre-sheaf of local section over B of M mapped to M. So I have that. So to make this precise, i.e., the global section of this pre-sheaf or of this sheaf are exactly the elements of M. Okay, so in principle, we start from a pre-sheaf. We associate a Boolean valued model. Then to the Boolean valued model, we associate a bundle, and we see that this in some sense corresponds to a sheafification process of the pre-sheaf we started with, and we ask, well, when is the pre-sheaf we started with already a sheaf according to this sheafification process? So this is the first question. And second question, it's of a logical nature, and is the following. So we have, we see that if we take a quotient, we have that M mod G models are of A1 G AN G, if and only if R of A1 AN belongs to G. Okay, what if one takes arbitrary tau formulae phi? So do I have in this case that M mod G models phi of A1 G AN G if and only if phi of A1 AN belongs to G? Well, this is a form of Losch theorem or a form of forcing theorem, and the answer really depends on the nature of the model M. So for certain models M, this is the case. For certain others, this is not the case. And actually, one of the results, which, I mean, it pops up in the literature oftentimes, but in disguised forms, is that, for example, this occurs when M is a sheaf, essentially when B of M corresponds to M. The global section of B of M are exactly the elements of M. Well, if this is the case, so if we are in the setup where question 1 is a positive answer, then we also have that question 2 as a positive answer. But actually, this is weaker. So we can have that question 2 has a positive answer, even in case that M is not a sheaf. Okay. Is this fine so far? Should I expand more on something?
Okay.
So I move on.
Move on.
Okay, so now I want to address, well, I mean, there are, I have a paper with many, where I touch several of these questions, and I will just now expand on one of these. So what I will try to describe is the process that, given a pre-sheaf, associate the Boolean valued model and then take this bundle and try to describe it as a sheafification process, a very natural sheafification process, which is actually corresponding to the sheafification according to the dense Grothendieck topology. And using this turnaround that I'm describing, one can give a very neat topological description of this shiftification. So let's say the outcome of the remainder of this talk is that using this analogy between Boolean valued model and pre-sheaf, one can give a very nice topological description of the shiftification of topological pre-sheaf with respect to the dense Grothendieck topology. What one finds usually in the when one talks about shiftification of a topological pre-sheaf, one is usually considering the soup Grothendieck topology. So the Grothendieck topology, which consider covers given by open covers of the space. So families of open sets such that the union is the whole space, while the dense Grothendieck topology is more liberal and allows families of open set as covers. If this family, when you make the union, you get the dense open subset of the space. Okay. So let me say definition given X tau topological space, the dense Grothendieck topology on, well, tau seen as a partial order is given by a subset of tau such that the union of A is dense in X. So A is a family of open sets. You take the union and you get a dense open subset. So this is the dense Grothendieck topology. And well, I will give the direct outcome of this functorial B functor. So the functor that given a pre-sheaf associate a Boolean valued model and given a Boolean valued model associate a bundle. So I will now just define the composition of these two functors directly. So definition given X tau topological space and F from tau up to set pre-sheaf. I want to define the bundle associated to this F, and I stick to the notation of the book by McLean and Murdick. What I do, I will put a 1 on top of the relevant operator. So in Grothendieck Murdick, it's defined the standard shiftification of a topological pre-sheaf according to the soup covering topology. While here I will do this shiftification of the topological pre-sheaf according to the dense Grothendieck topology. In general, the outcome is different. I will get a much larger bundle, but in some cases, the two operation overlaps. And I will say when this happens. So what is it? Well, the base space is changing. It's not anymore X. It's the stone space of the regular open set of X. What are the stalks? Well, the stalks are what you expect, the equivalence classes of elements according to the ultrafilter. Sorry, A belongs to tau and the regularization, sorry, and here. Regularization of A belongs to G. So for those who are not familiar, this is just the interior of the closure of A, but I imagine that I already lost those people if they are not familiar with this operation. Okay, So I have to define what is this. Well, what is this is a bit delicate because I matched the problem I had before. So it's given by those H such that the regularization of the union of the set of A in tau such that F restriction to A is equal to H restriction to A. This belongs to G. So you see, how do I check whether F and H are equal according to G? Well, I have to look at all the open sets where F restriction to A is equal to H restriction to A. I have to union those open sets up. I will get an open set which in general is not regular open, but then I take the regularization and I check that this regular open set is in the ultrafilter. Okay, and clearly I have a projection map that goes from lambda 1 F to the stone space, which takes my equivalence class F modulo G and gives the ultrafilter G. Okay, and now we can look at this space. I have to give the topology. Well, the topology is exactly obtained as you should expect. I'm copying the definition from Murdick-MacLean. So what I take local sections. Well, I just consider case in which the local section is defined on regular open set. I suppose, well, it's a bit, I suppose that I'm considering a space where the regular open set form a base. This is a slight, a slight assumption on the topological space, which is not always satisfied, but I mean, it's not particularly restrictive. And I can drop it at the price of being more convoluted in the definition. So what does this map do? Well, it takes a ultrafilter and it's well, actually, apologies. This is, I don't have this restriction, so I can take A belonging to the topology. So I take G, which is in A. I associate this the equivalence class of F, provided that F belongs to F of A and regularization. Sorry, well, here I'm apologies. G belongs to A is meaningless. A is an open set in the topology, and G is a ultrafilter on the regular open set. So this is the condition. So actually, yes, here I have to be more careful. So it's not A, it's the G such that regularization of A belongs to G. Okay, so now the definition is correct. Apologies. So what happens is, for example, if you are considering a complete Boolean algebras, in this case, the regular open set overlap with the clopen set. And what I'm doing here, I'm just defining my local section on the clopen set, and it suffices because the clopen set form a basis. Okay, and those are the local section of this bundle. And now we want to declare this local section open. So I take tau F is the topology, well, let's say the weakest topology. Which makes all f point continues on from stone B as well, from well, this object, let's call it NA from NA to lambda 1 F. Okay. Is this okay? Do you follow me to this point? Should I expand more? I've been a bit confused in this definition, so maybe there is something that has to be cleared.
Fine by me.
Okay, then I move on. I don't see objection. What happens with respect to the standard shiftification with respect to the subtopology? Well, the standard shiftification in general does not give an Hausdorff topology on lambda 1f, while in this case, since we have all this zero dimensionality which is popping in, we get Hausdorff. Actually, we get for any x tau, and any f from tau up to set, we get that lambda 1 f tau f is locally compact zero-dimensional Hausdorff. Bundle on stone of rho x. And it is non-compact if at least one stalk is infinite, because the stalks seen as subspaces of lambda 1f are discrete. So essentially, we are getting exactly the same type of argument that one sees in Murdick-McLean for the standard shiftification, but we get something more. We get a Hausdorff topology, because we have all these. I mean, we have added much more sections, local sections, and points in the stalks, and this helps in getting zero dimensionality and the hence Hausdorffness. Okay, so let's see what happens concretely with one example, and I guess that I will finish with this. So let's take the standard case. So f is given by well. Let me see A in tau Euclidean topology on R, CA equal f from A to R continues. Okay, so one can check that this is a sheaf, or f is a sheaf for the subtopology but not for the Grothendieck topology. Why? Well, for example, we have that Cn restriction n plus 1 n in Z is collating family for well, indexed by a cover of R for the Grothendieck topology. Okay, well, what is this Cn? Cn of x equal x, equal n for any x in R. So it's the constant function with value R. Why? Because what I'm claiming is correct, because if we union up this open set, well, we get R minus Z, which is dense in R. And so when we, but this is not a collating, I mean, this family is not a cover of R for the subtopology. It's a cover of R minus Z. Okay, so for the subtopology, there is no global section which is collating this family. Mm-hmm. But for the Grothendieck topology, there is. Okay, so what will be this global section? Well, we can guess it's the map that goes from, so the global section will go from stone of row R, so the regular open set of Euclidean topology into, well, real union infinity. And what is it? Well, it maps G goes to n if the regular open set n plus 1 belongs to G, and G goes to infinity otherwise. Okay, so what happens is that in order to describe the sheaf associated to describe sheaf associated to lambda 1f, we need to consider sections taking values in lambda 1f union infinity, which makes sense because lambda 1f is locally compact, so it admits a one-point compactification. So I do not have the time to describe how one is going to describe the sheaf associated to a bundle of this type, but it can be done. And let me close this talk, just saying that there is a natural, let's say, a junction theorem that shows that this operation I described is really giving a description, a topological description of the sheafification of pre-sheaf according to the dense Grothendieck topology. I don't have the time to state exactly the theorem because it needs still a lot of notation and terminology. So let me stop here. And thanks for the attention, and apologies for taking